In this video, I'm going to go through how to calculate the power of a component in a circuit. This is part of the presumed knowledge I have of students coming into IB Physics. It might serve as a refresher for some students who haven't seen it in a long time. Please take a moment and read through the success criteria for this video. So let's start with what we normally consider our equation for power. Power is the change in energy over time. And that's to help give us an idea of where these equations come from. Now, I'm not going to derive it all, but let's start with the first part of that equation, P equals VI. And if you've watched my other videos, you know that I talk about how voltage is a way of measuring the energy per charge. So that would be units of joules per coulomb. And current is the amount of charge moving past a point per second. So that would be measured in coulombs per second. Now if I put these together, like I have in the equation, you see that the coulombs cancel out and I'm left with joules per second, which is a watt, and that gives us power. Now, that's how I get to this first part of the equation here. In order to get the next part, or the final one, all we're using is Ohm's law. And if you remember, resistance equals voltage over current. So if I just take the first equation and I rearrange this, I get V equals IR. If I substitute that into my equation for power, I get power is going to be IR times I, or I squared R. Likewise, I can move this around and I could isolate for current first and substitute in and get the next one. So even though this comes from the potential difference in the current flowing through, say, a resistor, it's the same calculation in terms of power like we would have in our equations from topic 2. Don't forget the equations I have shown here are in our IB data booklet. Now, one equation that's not in the IB data booklet, and I really wish it would, takes this equation here and moves it around for energy equals power times time. And if I substitute in our equation there, I get voltage, current, and time. So if I want to know the amount of electrical energy given to any component in my circuit, I will take the potential difference across it, multiplied by the current going through it, and the time. Don't forget the time needs to be in seconds. This would calculate how much electrical energy is given to it, and if it's for a lamp, then that would be turned into light, and if it's a filament lamp, also heat. So one thing that does come up in topic 11 is about how we transmit our energy from our power plants to the local homes. And one of the ways we do this with transformers is we transmit as a high voltage but a low current. And that comes back to this equation that we're talking about. Power is current squared times resistance. Now, a common mistake many students use is they want to use the other versions of the equation, for example, V squared over R, and use the value of the, say, 10,000 kilovolts that the energy is being transmitted at. And that's actually not the power that you would want to be calculating. If we're doing this and we want to see the effect of transmitting over a long distance, you would actually need the potential difference from one end of the wire to the other. And that's usually a very small drop. But what we can calculate that's going to be constant, or fairly constant, would be the current and the resistance of the wire itself. If you wanted to know how much energy was lost due to the current being traveled over a long distance, that's the value we would use. You can see we have a small resistance of the wire. A lot of the times we assume they're perfect, even though they're not. But this does have it as proportional to the square of the current, which is why we transmit it at a low current. Well, please take one more look at the success criteria, and I hope this has helped you remind you of how to calculate the power of a component in your circuit.